let me show you with the calculator what we could do real quickly to confirm that work. So here's our calculator screen, and what I'd like to do is to quickly pop this function into the calculator, 2x squared minus 6x, and here's the function. We did the algebra on paper up here on the board, and then I need to use a viewing window based upon what I'd done on paper. So I'm not going to go very far to the left based on the sketch that we drew, so maybe minus 2. And let me go over to the right, maybe over to 5 or so, and put tick marks every one. And then vertically, I need to make sure I go down below minus 4.5, a little bit lower. So let me maybe make it minus 6, and maybe take it up to plus 3. Well, how about plus 4? And put tick marks every one. So jot those 6 numbers down if you need notes. Minus 2, 5, 1. Minus 6, 4, 1. And then graph. You can see by setting the scaling, we have been able to nail the x-intercept at 3 and at 0. And you can see it bottoms out. It looks like symmetrically here. And what I wanted to do, we've done something similar with our circle in the last class session. But what I want to do here is I want to show you the table feature. So we could build a table of values which are the function input values with their associated calculated output values. And the way we do that is on our graph key on the calculator, which is in the upper right, you'll notice on the case of the calculator it says table. So you use your shift key to activate table. And I want to do table set first, though. And table set actually is on the window key if you shift on your window key. So let me start at, say, -1 and let the table increment by whole numbers. So what I do is I do table start, and this is assuming the x value is -1 to start. And we're going to let the table change by increments of 1. And now I'm going to go look at the table. So here's a quick way that you can draw, or you can build a table of values. And so notice that it appears to bottom out notice the symmetry here between x equals 1 and 2. Notice the symmetry of the y values. And so if I change my table set increment, what might be a good choice for the stepping point instead of going every 1 here? Every what? 0.5, because we know that the vertex sits down there at 1.5, right? At 1.5. So why not let the table increment at a half step? So go back to table set, change the increment to 0.5. And now go back to your table, and you can see where it bottoms out. And you can see the symmetry. If I scroll down here and you look at the numbers here, you can see the symmetry. See the symmetry in these numbers, and they're to either side of 1.5. And here's the minimum value. So this confirms the work we did on the board. Feel good? All right? And then you can always go back to the graph. Okay. Let's come back to the board for a second. So come back up here to the equation of the function and get the control room to catch up with me. Okay, we're back here at the function, 2x squared minus 6x. Can you do a little bit of algebra on that? Camera? They're looking at my watch. There we go. Okay. Okay. 2x squared minus 6x. And what we could do is factor out a what? 2x is common, isn't it? So we can use our distributive property in reverse, and we can factor out 2x and be left with x minus 3. I'm going to erase a little bit of this work we did earlier down below here because I want it in part of our graph, because I want to point out an item or two that'll be useful. So here's our function. This is called the general form. This particular problem allowed us to factor it. This we call the factored form. What can you see by looking at that factored form that relates to the sketch that we drew? What can you see from the factored form?
That the 3x minus 3 coincides with the x and x.
Can't you see the zeros? Do you see the zeros by looking at this factored form? If x is 0, doesn't that make y 0? And if x is 3, doesn't that make this whole thing 0? Yeah, so you can see the zeros real easily from the factored form. What can you see from this general form? Well, I'm going to have to help you probably, because you may not remember the fact that it's a parabola, because you identify it from your background as knowing it's a second-degree polynomial. You know it's a parabola. And you know that it opens up. Why does it open upward, left and right? Because the leading coefficient is positive. Doesn't this thing look like an x squared graph? Doesn't it look like the familiar y equals x squared? This is called an elementary function that's had something done to it. And so it has a behavior like x squared, and this 2 just simply is going to magnify it a little bit. And then this is going to alter it a little bit too. But nevertheless, it's still going to have the character of a parabola, and it's going to be opening upward. Opens upward. So you can see these two things from the general form, and you can see the zeros from the factored form. We'll be doing that quite a bit in the coming weeks. We have a few minutes left, 5 minutes or so, and let me take a look in the book and see if there's any topic in this material that I may have missed. I see one thing that would be useful. All right, let's stick with that same parabola. What would f of a be for that particular function? We had our function 2x squared minus 6x. What would f of a be?
2a squared minus 6a.
Right. All we're doing is replacing our input with a, right? And this is a recipe, remember, and this is our input right here where you see this x. So you square the input, you'd multiply it times 2, and then you take the input times 6 and subtract that from the original, from the front end term, right? So if you replace the input with a, you're going to get 2a squared minus 6a. And we did it earlier with a couple of numbers, didn't we? Okay, try this. F of x plus h. What are we doing with our input now? What's the input become?
X plus h.
The whole, everybody hear this? Because about a third of you won't remember this when you see it in homework. This is the input, whatever's sitting here in parentheses. And so now what you see in parentheses is x plus h. So I'm now going to replace my input in my recipe, or in this machine, with x plus h. So I go in here and I square the input, but my input is now x plus h. Stay with me. Stay focused. Minus what? 6 times x plus h. Don't forget the parentheses there, very important. Now, let's clean this up. Let's expand this thing. We're going to have twice, and we just went through binomial square, folks. Square the first, take the product, xh, and double it. So I'm going to write it as 2hx plus h squared minus, I'm going to go ahead and distribute that, 6x minus 6h. Be careful distributing the negative 6. Then we're going to clean it up. Actually, it's kind of a mess, and I don't think it's going to clean up. So we end up with a 2x squared plus 4hx plus 2h squared minus 6x minus 6h.
Is that the right order to put all those?
No, it's not the wrong order either. It's just
Whatever.
I just wrote it. Okay, good question though. Now I have about 3 minutes left or so. So what I'd like to do is to build something that's going to get you really excited. I want us to create the following. F of x plus h, and I want to subtract from it the whole machine recipe, and I want to divide that by h. Let's do it. So we have this mess we just created up here for f of x plus h. So we have 2x squared plus 4hx plus plus 2h squared minus 6x minus 6h. Now watch out. I need to subtract from that mess the entire original recipe. So be careful. When we do the subtraction here, folks, we're going to be subtracting the quantity, 2x squared minus 6x. So that becomes minus 2x squared plus 6x. And that whole numerator is divided by h. If we did our algebra correctly, no matter what function you pick to do this kind of to create this kind of a fraction here, this is a special kind of a fraction. I'm going to talk about it at the beginning of the next class session. It's a very special thing. If you do your algebra correctly with this mess, you're going to notice something that happens. What do you see in the numerator that's going to happen?
2x squared goes away.
The 2x squared disappears, and the 6x, negative 6x and positive 6x will go away. This portion of the numerator will always disappear if you've done your algebra correctly, no matter what the original function happened to have been for this special thing. Hey, how much time do I have left? 1 minute? Okay. Good. Let me just mention what this thing is real quickly, and then we'll go into a little more detail about it tomorrow in the next class session. If we have a parabola similar to the one we just had, if I go to some location x, that could be anywhere on here, I have a location on this function that is f of x in its y value, right? And what if I added something called h to it and maybe took me over to here? Maybe this distance is h from here to here. This would be location x plus h, wouldn't it? And what's the height of the function at this location? Isn't that f of x plus h in height? If I use this input, isn't this the height? This is the y value right there. And so the difference in the y values here is the numerator of that relationship. This y value minus this y value is that change in y, and this horizontal run between them is the change in x. And what we've got here, that equation we just came up with over here, is the slope between this general point and this other point that's over at a new location. This thing is called a difference because you can see the change in y and the change in x in that equation we had, quotient, difference quotient. And so the slope between the 2 points is what this expression turns out to be. And in closing, I could now see a common h term here, notice, and wouldn't that divide out? The common h in each of those numerator terms that were left, and I'm going to be left with 4x plus 2h minus 6 for this thing I'm calling the difference quotient. All right, so I reviewed some algebra with you today, showed you some different features of graphs using a parabola as an example. And we also talked a little bit more about domain and range, and then we came up with this thing called the difference quotient. So we'll see you next class session.
So is that change in x the same as h? Or
Yes,
is that h?
yes. Yes.